Hello and welcome to the next video in the series. In this video we're looking into static and kinetic friction and learn how to calculate it properly and have some particular definitions that go along with it to make us understand it better, to help us understand this. I've drawn the arrow in red for friction, and you'll notice that it is on the bottom part of this block. We'd assume that this is kind of similar to a book sitting on a tabletop, and the book is going to slide across the tabletop. I'm going to assume that this is my force applied to the right. And friction, which we draw with a scripted F, is working opposite to that force, because friction doesn't like things to move. It resists motion. Something else we can gain from this diagram, that would be the normal force, that is supposed to be an N, and this is your force of gravity. And by the way, those are equal and opposite, because there is no motion up or down. There's no vertical motion. It's not like it's flying off the table or falling through it. So, no motion vertically, but there could be motion in the horizontal direction, means there could be a net force, could be an acceleration of some sort. So we'll go over and through these terms relating friction to static and kinetic friction, and also talk about the coefficient of friction relating it to normal force. And by the way, the term equilibrium fits very nicely right here because the force of gravity and the normal force are currently in equilibrium. Alright, friction is a resistance to motion caused by the interaction of two surfaces. It is literally caused by bonding between these two surfaces. So when you leave an object sitting still, bonds start to form between one object and another, between the book that you put on the table and the table itself. These small bonds, which are nothing for us to break, we push it and they're immediately gone, are something more important on the smaller scale, on the molecular scale. But there are actually bonds forming between objects. And over a long period of time, these bonds can become very strong, and the surfaces can kind of start to meld together. So, in extreme cases, you can actually have the surface sticking to the other object because they're so strongly attached. Drag forces are another type of friction, but they're caused by the interaction between an object and a medium, and these are ones that we're going to cover later and get into more detail as we go into that section of the unit. But for now, we look at static friction, which is a type of surface friction, so between an object and a surface, and it's a resistance to an object which is not moving relative to the surface. So it's a resistance to this object, and this object is not moving yet, and it doesn't want it to. Static friction doesn't want the object to get anywhere. It doesn't want it to move at all. It wants it to stay at rest relative to the surface. Now that's a complicated definition. So to simplify that, what we can say is it's basically the friction that keeps an object at rest when on a surface. So, just keeps the object stationary. It doesn't want to move. And obviously this is above and beyond inertia, because inertia is the resistance of an object to a change in state of motion. So when it's at rest, it already doesn't want to move. But on top of that, there's also static friction forming between one object and the surface it's on. Kinetic friction is the resistance to an object that is in motion relative to a surface. In other words, the object is moving and there's some resistance to that motion. It's kind of like you have a book on a tabletop and we can confirm that this thing is going to the right. Well, then friction must be working to the left, opposing the motion. And that's kind of what the basic idea is saying, is that it's just a resistance that an object encounters when it's in motion, and it generally attempts to slow or stop it. It's opposite of the velocity every time. It's opposite of the motion. Keep in mind, a quick review, this is the way it's moving. This is kind of which way it's actually heading. So the friction always has to work opposite of whichever way it's going. Alrighty, well, there's a key idea here. Static friction is generally greater than kinetic friction. Very rarely they're equal, which is why I say generally greater. Sometimes they're equal to. Kinetic is always less than, is the thing though. So you can basically say that static friction, if we say that F is for friction, is greater than or equal to kinetic friction. That's a way to write it down mathematically if you wish. They're generally not equal. Generally, static friction is greater, and usually fairly significantly, because there's more time for the bonds to form. When an object is stationary, not moving, there's more time for bonds to form, which means there's going to be more bonds, which means a greater force that you have to break to move the object. When an object is already sliding, already moving, the bonds don't have time to form, so they're very weak. It's very easy to keep that object going. And we're going to find that out in our lab that we do soon. Something I'd have you consider while we move on to the next part is consider the idea if you try to push something very heavy, something that's flat, not a surface. When you try to push something that's very heavy that hasn't moved yet, it's very hard to start it moving, but once it's going, it's way easier to get it going. It's kind of just like get it into motion, and that's way easier to push. That's related to the whole static and kinetic friction idea. So the equations we use here, there will be two. Here's the equation for static friction. It is an exaggerated, well, it's a script F. Mu, which is not drawn strangely, it's actually like you draw a U, so here's my U, and you got a little nose off the front of it. So it's like drawing a U, except it's got a little nose off the front. That is the Greek letter mu. So this is for static friction. And static friction, this is actually standing for static force of static friction, we should say. And mu s stands for the coefficient of static friction, which we're going to get into shortly. I'll talk about what it is. N is for normal force. Some key ideas: force of friction is a force, which means it's measured in newtons. Coefficient has no units. And the normal force is a force measured in newtons. So we're going to change some things. Now we're going to look at the equation for kinetic friction. And you'll be amazed at how much it very much changes. Okay, so I fibbed. Basically, it just changes the letter. So in this case, the force of kinetic friction is equal to mu k times n. And Fk, the scripted F with a sub k next to it, really just means force of kinetic friction. And when you look at mu, sorry about that, that should be mu k. It's the coefficient of kinetic friction, and n is for normal force. Still, same thing. Basically the exact same equation. So something must have changed. The thing that changed is the coefficient, because the coefficient is different between static friction and kinetic friction. The coefficient of friction, mu. So mu is basically a factor by which you multiply the normal force that represents how sticky or grippy a substance is, or surface is. So it's a factor which represents how rough or smooth the surface is. I say sticky or grippy, which is kind of an interesting idea, because basically it's the idea that your shoes are pretty grippy, right? Your shoes are very good at gripping the ground. They're not very slippy. Whereas if you had ice skates on, they'd be very slippy. You'd want to slide with those. Or if you were on a wood floor and you got on a nice pair of socks and your floor and you are very slick, you can slide across the floor very easily. So a low value would be very slippy. We'll call a low mu, or a low coefficient, slippy. Another way to put it more realistically is it's very smooth. It tends not to have a lot of places where bonds can form. Whereas a high coefficient means it's a very grippy surface, or it tends to be pretty rough, because imagine taking those same socks that would slide so nicely across a hardwood floor and then try doing that across concrete. It doesn't work out so well, because you have a much more grippy surface. There's a much more gription between the two surfaces. So high value versus low value, that's kind of a general idea. And the coefficient tells you basically how sticky or grippy is the surface. How likely are they to bond to each other? In these examples, we'll compare mu s and mu k. You get an idea on why the coefficient, or why the force of static friction is greater than the force of kinetic friction from this. For tires on a nice dry road, the coefficient of static friction is 1.0, and the coefficient of kinetic friction is 0.8. Clearly, coefficient of kinetic friction is less. Now, here's something to think about. When your tires are rotating, it's static friction as long as your tire isn't slipping. So in other words, when you're just driving normally and your tires aren't spinning out on the road and just kind of like, you hear that burning noise, then you have static friction. When the tires spin out or can't get gription and they keep just spinning out of control, that's kinetic friction. On a wet road, coefficient of static friction is 0.3, a huge decrease from what it was before. You can even think about it percentage-wise. Before, you basically had 100% effectiveness of the tires on the road. Now 0.3 compared to 1.0, kind of like 30% is effective. When you look at mu k, 0.2, large difference, and still coefficient of static friction is greater than the kinetic. When your tires are spinning out of control, they're very much less effective at gripping the road. Go figure, you already knew that intuitively, but here's the reason why. The last one's an estimate. I think I have this right, but I have to go double check and I'll let you know if it's different. But if you think about Teflon on steel, like you take a Teflon pad and put a piece of metal on it and shake it around, it's not going to stick or grip at all. This is where we see a situation where the coefficient of static friction and kinetic are equal, and that means that the force of static friction in this case is equal to the kinetic friction. There's no difference between the two. Static would have been greater generally, but in this case this is one of those equivalents. So obviously Teflon is kind of handy if it's Teflon of steel, and it's one of the reasons why they thought about trying to coat objects that are frictional. In other words, like parts of your engine, they need to be constantly moving and get very warm. Why not try to coat them in something that has a very low coefficient of friction, so you have to apply less oil to it and have to maintain it less? The theory is out there, but obviously not necessarily practically applicable. A handy trick I've taught people to memorize the equation for friction is it looks like you wrote fun down. And all you have to do is put an S next to it when it's static, or a K next to it when it's kinetic. So friction is fun. Something you can think about here, in the wintertime, people add weight to their vehicle. Well, why? Because they don't slip as much. Well, you already knew that, but let's think about it from physics. You know that when you have a certain amount of weight, there's a force of gravity, and normal force has to be equal and opposite. Oh, we're going to focus on that idea. What if I was to increase the force of gravity? What would I have to do with the normal force in this case? Well, it'd be huge. It'd be much greater. So, if I were to increase the normal force, I would therefore increase the force of friction. So that's what people are doing in the wintertime when they add weight to their vehicle. They are trying to increase the weight that pushes on the ground, which therefore increases the normal force back on their vehicle, which gives them more friction, more grip. Alrighty, let's try this problem out. Please read this and then begin it, and I'll go through it. So our block has a mass of 15 kilograms. And by the way, whenever we're in this unit, best thing to think about is drawing a free body diagram whenever we get a chance. Coefficient of friction between the block and the surface is 0.4. So I'm not given whether it's kinetic or static, so we'll just keep it as is for now. Find the acceleration of the block when the person pulls it with a force of 75 newtons. Okay, I probably want to draw this. It looks like I have a force applied, but I don't know where to put it in the equation or in anything yet, so this isn't really good yet. I better draw a picture and see what I got going on. I know if it's on a solid surface, there must be a force of gravity from Earth, and there's a normal force that's equal and opposite to that because it's on that solid surface and it's not falling through it. I'm going to assume that they're pulling it to the right. I can get away with doing that. And now it's accelerating. So now we can answer the question, is this static or is this kinetic friction? Clearly it's kinetic because it's in motion. So I'll draw in my friction arrow. And by the way, it's always drawn where the contact with the surface occurs. So it's on the bottom in this case. And I can now look at this and figure out, well, what am I trying to find out? The acceleration. Well, the acceleration in this case must be, hopefully you recall from last time, basically this force applied plus my negative kinetic friction must equal the net force. And since the net force is equal to mass times acceleration, that's where I'm going to get my acceleration from. So we just have to calculate this. So let's see what we get. The force applied was 75 newtons plus, or well, minus friction. Hiccup there. How could I calculate friction? Let's see here. What if I was to say force of kinetic friction is equal to coefficient of kinetic friction times the normal force? I surely could do that. So, first off, we know the coefficient. It's 0.400. I don't know the normal force, and that's not good. So I somehow have to find that, but we do recall normal force is equal and opposite to gravity. So if I was to solve what is the force of gravity on this, which force of gravity is just mass times gravity, I could take my 15 kilograms times 9.8 meters per second squared and find that my force of gravity is 147 newtons. If the force of gravity is 147 and it's equal and opposite to the normal force, then 147 newtons must be the normal force as well. So let's go way back down to the lower right where we started. I'll multiply this by my 147 for the normal force, and now we can figure out what the force of kinetic friction was. I end up getting 58.8 newtons. Alright, well now I can plug that value into my equation here, because I was going to subtract force kinetic friction, but I didn't have a value for it. Now I do. So I can say, well, this must be 58.8 newtons, and that's therefore equal to mass times acceleration. But I know my mass. It's 15 kilograms. I don't know A. So we do that math. When we subtract our 75 minus 58.8, we get 16.2 newtons, and that 16.2 newtons must still be equal to 15.0 kilograms times acceleration. We divide both sides by 15 kilograms, and we should find our acceleration is 1.08 meters per second squared. We could say to the right, because in my diagram, I had this going to the right. And that would give me a direction to this. So what was the acceleration of the object? 1.08 meters per second squared to the right. We started off by finding out that the force of gravity had to be equal to normal force after we drew a free body diagram, obviously. And then we said, well, there must be a net force acting on this, because if I added the force applied and took away what friction is trying to take away from it, we would find out the net force acting on it. And from finding the net force acting on it, that must be equal to ma. We solved for A, and we found out this 1.08. We did a separate calculation on the left, because at some point we needed to know, well, what's the value in newtons for the force of friction? We did that work, and then we plugged it in the equation from there. At this point, you can stop watching the video if you just wanted to get the basics. What I'm going to do next is do a much more complicated example. So please stick around if you're interested in watching this part, but at this point you've gotten the basics. You should be set to go. Please read over this problem and underline the key details. I'm about to shrink the size of it so it's easier to read and so I have more room. Of course, when I say easier to read, I just mean smaller and simpler to work with for me anyway. So, from here, we know that there is a block. It is mass of 20 kilograms. So, I'm a big fan of writing down everything I know when I know it. Sitting on a level surface. Convenient. The coefficient of static friction between the block and the surface is 0.35. So that makes mu s equal to 0.350. The coefficient of kinetic friction is 0.3. Okay, so I'm going to need both of them in this one. That's a challenge. Find the following. What is the minimum force needed to move the block? This takes some thought, and that's the whole joy of physics thing, is getting a situation and problem solving through it until you get a good idea of what you're doing, and then you find the answer. It's quite a glorious thing. From here, well, I'd draw a free body diagram if it were me, because I want to figure out, well, what am I looking at here? I know I got a block on a solid surface that's level, so probably got a force of gravity that's equal and oppositely opposed by some normal force. There's some friction working on it. To move the block, how much do I need to move it? Well, it must not be moving yet. And if it's not moving yet, then I'm trying to break static friction. So, if I was to say, what is static friction? If I was to apply anything greater than the value of static friction, it'll move. Because I just have to break static friction in order to get the object to move. So we need to figure out what the value for static friction is. Static friction is calculated using this equation. I already know the coefficient, so that's convenient. So I could already start writing things into the equation. And I run into a hiccup at the normal force. So let's look into how to calculate that. It's rather easy, and chances are you've got a good idea as to what to do. I'm going to move my work down to the other side so that I can continue what I'm about to do up here by the force of gravity. Since the normal force is equal and opposite to gravity, I'm going to take my 20 kilograms, multiply that by 9.8. I'm basically doing the calculation Fg is equal to m times g. When I do this, I find out that the force of gravity is 196 newtons. If the force of gravity is 196 and it is equally and oppositely opposed by the normal force, then the normal force is also 196. Which means I can put that 196 into my equation down here, and I can figure out what the force of static friction is for this object. And then all I have to do is apply anything greater than that. I find that the value is 68.6 newtons. So the question was, what is the minimum force needed to move the block? I found the force of static friction. That's not the answer. The minimum force needed to move this is anything greater than 68.6 newtons. Not equal to. If it's equal to, then static friction can resist that. I must apply a force greater than 68.6. Anything greater than static friction, I'll break it. It will move. For the next situation, once the block is moving, what is the minimum force needed to keep it moving at a constant velocity? Obviously, in your work, I would have you draw this again if you so choose, but a lot of this work is still solid. I'm going to get rid of what I've written down for static friction, and I'm just going to summarize this to 196. So I just want you to be aware of why there are changes to the diagram you see. And now the next situation is asking us for it's moving. So now I'm changing that to an FK. If it's moving at a constant velocity, that means it cannot be accelerating. And if it cannot be accelerating, then we can't have a net force, because a net force is equal to mass times acceleration. We can't have that, which means the net force must be 0. These two must be equal opposite. My force applied must be equal to the force of kinetic friction. That way it is not accelerating. So all I have to do now is just calculate, well, what's the value for kinetic friction? And to do that, seeing as we already did all the legwork before, all the real serious problem solving was already done in the problem, aside from figuring out that that had to be a constant velocity and the force had to be equal and opposite, we've already done the math work. Now all we have to do is just plug that in and multiply away. Force of kinetic friction is 58.8 newtons. And you'd think you'd be done. But the question said, once the block is moving, what's the minimum force needed to keep it going? It doesn't ask what's the value of kinetic friction. So I may have found the value of kinetic friction, but the important thing to say is that the force applied must be equal to 58.8 newtons. Now that's to keep it moving. But the question may come up right now, what if I pulled with more force than just kinetic friction? It'll still be moving, but not at a constant velocity. So in order for it to be a constant velocity, the forces must be equal and opposite. The force of kinetic friction must be equal to the force applied. If you have any questions on this, please let me know. Thank you for your time.